Hi folks, we are on the Unit 1, Day 8, continuing on with our lesson on operations with algebraic vectors. So in this example, number 4, we're given 3 vectors in R2 and asked to calculate the magnitude. Now remember that these vertical lines mean magnitude of the stuff inside. So we are going to need to actually calculate what this new vector a plus 2b minus 1/3 c is, and then we'll find the magnitude of that new vector. So we usually use an R for resultant, the vector you get when you add or subtract multiple vectors together. So I'll do that. I'll say that R is equal to a plus 2b minus 1/3 c, and then I'm going to put in my a, b, and c values from above. So it's the vector 4, -2. Remember, these are not points, they're vectors. And -6, 2 plus 2 times -6, 2 minus 1/3 of vector 6, 3. So this becomes vector 4, -2 plus vector -12, 4 plus vector -2, -1. We could have left that as a minus and not put the negative in. That would have worked fine as well. So remember, when we're adding vectors, we can just add the x components and add the y components. If we're in R3, then we have to also add the z components. So here I get 4 plus -12 is -8. Minus 2 more is -10, and then I'm at -2 plus 4 is 2 minus 1 is 1. So that's my new resultant vector, but I'm not just asked for what that vector is, I'm asked for the magnitude of that. So I'm going to calculate the magnitude of vector r, and vector r goes to -10, 1. So using the Pythagorean theorem, it has a vertical movement of 1 and a horizontal movement of -10. So the hypotenuse of that will be the square root of 101. And we're going to leave that as an exact value unless you're dealing with something that is a word problem. Like, for instance, if you were finding a velocity, then you're going to take the square root and tell me that the velocity is 10 point something kilometers per hour. But if this is more theoretical, we want to leave it as accurate as possible. So we have these vectors a, b, and c drawn here. So vector a is here, and then vector b is here, and then c is the red one over here, 6, 3. So what I want to do is to kind of draw a representation of what a plus 2b minus 1/3 c would be. So vector a plus 2 times vector b, I'm going to add 2 of these vectors to the head of vector a. So vector b goes 6 to the left and 2 up. So I'm going to do that twice. 6 to the left and 2 up, and then 6 to the left and 2 up. And I would get to that point there. So I'm going to take a ruler and draw that in. You'll notice how that's parallel to the vector b that I have here. Starting at the head of vector a, I'm drawing in -2 times b. Okay. The next thing I want to do is add on 1/3 of c. Sorry, pardon me, -1/3 of c. So this is vector c. I want a vector 1/3 the size going in the opposite direction. So 1/3 the size would be that big and going in the opposite direction. So I'm going to add that in there. So that's -1/3 c. So this vector here to here is my resultant. So I'm going along a, then 2 times vector b, and then -1/3 times c. So I will label in the resultant vector that would end up at the ending point there. And remember, I'm going to start that resultant from the origin, from 0, 0. So you can see kind of in this diagram how that resultant ends up looking. So it's going -10, +1, which is what we had when we did our calculations. So the next example is moving into R3. We're just looking for vector AB in component form and in unit vector form. So remember, if we're looking for vector AB, we have to subtract. It's x2 minus x1, y2 minus y1, z2 minus z1. And again, the order is really important here. AB is a different vector from BA. So I'm going to write, again, just for today, I'm going to be writing out what operations I'm doing. So if people are looking at this note or kind of unsure of where I'm getting things, you can kind of see it, but you absolutely don't have to do that. If you subtract in your head and get it right, this would be like a 1-mark question on a test, so I'm not really concerned with you showing that work. So here we get vector AB is 3, -1, 1. So in the x direction, I'm moving 3 units. In the y direction, I'm moving -1 units. And in the z direction, I'm moving +1. Okay. We can also write this in standard unit vector form, which tells me that AB is 3 times I hat minus j hat plus k hat. So 3 in the I hat direction, in the positive x direction, -1 in the positive y, and +1 in the positive z. Okay. Again, we can use our same vector operations to simplify things written in this unit vector form. So if I want to find 6a minus b, I'm just going to substitute in the expressions for a and b. These can be written as a linear combination of the 3 unit vectors here. And then that allows us, whoops, I need a 6 times this, and then minus the b. That's going to allow us to simplify this in with like, kind of collecting like terms, adding up equal vectors here. So I'm going to multiply this vector A by the scalar 6. So then it will go 18 in the x direction, -12 in the y direction, and -6 in the z direction for our k hat. And then we're going to subtract this, so I get -5 I hat plus j hat minus 6 k hat. And now I can add equal vectors together. That's really the benefit here, that we can write any vector in terms of these 3 basis vectors for 3-dimensional space. If you can express every vector in R3 as a combination of I hat, j hat, and k hat, then it's very, very easy to simplify them and do vector operations, because we can write them as a sum of all of them in terms of these same 3 vectors. So we have 18 I hat minus 5 I hat, so that gives me 13 I hat, -12 j hat plus 1, so minus 11 j hat, and then -6 and minus 6 more is -12 k hat. This could also, depending on what format you were asked for, this could also be written in component form. So this would be the vector from the origin to the point 13, -11, -12 in 3D space. One last example here. For points A and B, we're looking for vector AB and the magnitude of vector AB. So the first step, finding this vector. And again, you don't need to necessarily show this work, but the order is really important. Making sure, like, I know it's a silly thing, but just be careful with double negative signs like this 5 minus -10. You don't want to make a minor little calculation mistake that's going to kind of follow you through the whole question. So then that's -3, 15, 1. So that's vector AB in component form. It doesn't ask for a certain form, so I'm fine just to leave it like that, but I could rewrite it in unit vector form with I hat, j hat, and k hat. The magnitude of this is going to be basically the square root of x squared plus y squared plus z squared. So the square root of -3 squared plus 15 squared plus 1 squared. So that's 9 plus 225 plus 1. So I guess I'll show my work because I already wrote a very big square root. And the square root of 235. So the calculations here are not that complicated, but you really do need to make sure that you understand those, the formulas. And I would say that the biggest place that people mix up is remembering the difference between when you're subtracting the x values, finding a vector from point A to point B, you're doing x2 minus x1. But when you're adding together, say vector u plus vector v, you're going to add the x values, add the y values. So just make sure that you're clear on the difference between those two actions. And that is it for day 8.